Once we've understood and used the arithmetic sequence and the formula in different contexts, now we can move to the sum of the arithmetic series. So we don't say arithmetic sequence, we're saying that we want to add the series of terms in the arithmetic sequence. So a series is when you write the arithmetic sequence with pluses in them. So with the arithmetics, we take the finite sum. What I'm going to do is spend a few minutes in the beginning explaining where the formula comes from, and then complete a couple examples afterwards. So it's important to understand how the proof is constructed, not something you would be examined on, but it's good to understand or get familiar with how proofs are done. So first part of the proof is, let's set up, I want to add a finite sum. I want to add all the numbers up until n. So this is the series that I have for my arithmetic sequence. I'm going to write it as a series as u1, u2, u3, u4, and so on. Now we have a way of writing each one of these using the arithmetic the nth term formula. So what I'm going to do is replace each one with the correspondent general formula. So u2 is basically u1 plus d, u3 is basically u1 plus 2d, and so on. And un is basically u1 plus n minus 1d, which is the general formula. Now, what I'm going to do is something a bit odd, which is just flip or reverse the order. What I'm going to do is start with here and go backwards and end at u1. So we're going to start with u1 plus n minus 1d and go backwards. So we're going to go un minus 1, un minus 2, and just go backwards. So might look a bit odd, but all we did was go backwards in the sequence. So this is the last term here, and this is the second to last, and so on, and we go backwards until we get back to u1. Now, what we're going to do is we're going to add them together. Now, this is going to be a bit odd, so what I'm going to do is explain how it's going to go. So what we're going to do is add this with this. So the left-hand side is just going to be 2sn, if I'm just adding them together. The right-hand side, interestingly enough, let's just take this part first. Or actually, let's take, so we said this will be 2n, and what we're going to do is we're going to take this part first. And if you look at this, and if I'm going to add them together, it's going to end up being 2u1 plus n minus 1d. So that's one part. Let's try adding this section. So the second term, the second value in this sum and the second value in this sum. Now if I bring them together, I have u1 plus d, and I have this part, and if I expand it out, I'm going to get, so plus u1 plus n dn, if I'm expanding out, minus 2d. And if I simplify this whole thing, I'm going to get 2u1. I have a positive d, dn, and then minus 2d, so that's going to simplify to minus d. I can factorize this out and get n minus 1, or for convenience, n minus 1d. And notice how they're exactly the same. I can repeat the same thing with the third term here and this third term. And if I expand this out and add these together and simplify, again, I'm going to get 2u1 plus n minus 1d. And it's going to be the same every time I add them together. So remember, we're adding these two. Every time we're adding two together, we're getting the same exact thing. So what you end up with is just the same exact replica of the whole thing. So we're taking first, second, third, fourth, fifth, sixth combination, and so on. So we get the same exact simplification. Now, how many combinations did we do? We have n of them. Remember, we're adding n, so we actually started with n of these. So in total, it's basically you just rewriting this as if this was x, 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 and so on. How many x's do you have here? You have n of them. So it's nx here. So this is your x. So we're repeating this sum, we're adding it n times. So the left hand side was 2Sn and the right hand side is n times the sum. So what you end up with is this, and then I want the sum on its own, so I have the sum of the first n terms of the arithmetic sequence is n divided by 2, 2u1 plus n minus 1d. So you can repeat this video, try to understand what's going on, but basically it follows the story of Gauss if you want to look into how he did the summation of 1 up till 100. If you can figure that out, then this proof should be easy. So this is if you're adding the first 80 terms, so 80 is going to be here, so your n is going to be 80, and then you substitute all the values here, and what you're going to end up doing is adding the first 80 numbers. It always starts from the beginning. Now, this is the general formula, and if you notice, it kind of looks similar to the general formula, this is the general formula for the sum of arithmetic sequence, and it looks like the general formula. So actually, we can rewrite this into this. So instead of taking 2u1 n minus 1d, I take 1u1 and then add the last term I'm adding. Now, these are exactly equivalent. You can use one over the other. But it depends on the question given. So I'm going to do two questions and I'm going to show how one formula is actually easier than the other. So I have the first 4 terms of this arithmetic sequence and I need the sum of the first 80 terms. You can pause this and try this on your own. So let me lay out everything I have. I have the first term, common difference I can find by just subtracting, and then I know that I need to add up until 80. So I need up until n is 80. So S80 is 80 divided by 2, and then substitute all the values that I need, simplify, and get 9,880. First formula, very simple. What the second formula requires is that you should know what the 80th term is. We don't know what the 80th term is. So if you want to go the long way with the second formula, what you're going to have to do is actually find the 80th value. So what we're going to do is find this had to be 80. Okay, so U80 is equal to 5 plus 3, 80 minus 1, 242. So we know that the last term is 242, so what I'm going to do now is just take 80 divided by 2, same thing, but now the first term plus the last term I need to add, and that's going to give me 9,880, and that's the same answer. But as you saw, it's easier to use the first formula. Now, using summation, just to link to previous lessons, what we're doing is we're adding up the same term up until 80. So this is the general formula, and what we're doing is we're adding the term of each of the values we get in the general formula until we get to 80. So this is the sum of the first 80 terms of the sequence. So these two are equivalent, or it's the equivalent notation. Now, let's try this. We need to find the sum of this series. Now, what we have is the first term, we have the common difference, and we have the last term, but we don't have the position of the term. So if we have the last term, it's easy to use the second formula, but I still need the position. So let's do an extra step where I actually find the position using the general formula. So using the general formula, I'm substituting everything in. I need to find the n is going to be 22. So 81 is the 22nd value. Substituting in this formula, because it's easier to do than the first one, I get 22 divided by 2. This is the first term, this is the last term, and I'm going to get 858. Hopefully this was clear. Understanding, again, similar to a general formula, understanding the basics of using the sum of arithmetic series will help you explore more complex examples on adding values in the arithmetic series or the sum of the first n terms of arithmetic series sequence.